Let's go back to chapter 19 and begin this.
Sorry, so if we're submitting the problem sets on Sunday on Dropbox, can we submit JPEGs of images?
No, one PDF. That's what I'm saying. Yeah, so like if you have hard copies, you take like 7 or 8 pictures, you use an app called CamScanner or GeoScanner or something, and it makes a PDF.
Oh, yeah.
And I just upload that, Dropbox. One document in order, not 18 attachments of JPEGs. Okay? Trimmed and everything. You know, I want it to look good. Like I don't want to see the desk of your, room. I want to trim it. Good. Just use that. Hey, what was? Okay, come on. What was chapter 19 about? Chapter 19. Current, then resistance, voltage, and then power. Okay, so let's talk. Current. Current is? Current is? The flow, I. Current is really how much charge passes a given point in a time period. Remember, it's Q over T. Current is really how much charge flows through a location in a given time period. Q over T, that's what current really is. It's the flow, but you should be able to understand the electrical definition of current. Don't just say the flow of electrons. Okay, so it's how much charge physically passes a given location in a given time period.
Okay, what's Q?
Q is the amount of charge. Like little q, I put big Q here. This means like, in this case, if there were 20,000 electrons passing that, you would do 20,000 times little e. That's the amount of charge in coulombs. Okay, so this measurement is coulombs per second, which is known as an amp. Okay, that's what the units are. The units are coulombs per second, which are amps. Marco.
And when it's in electrons, you have to, you multiply.
So if I told you 85 electrons pass the given point in 3 seconds, 85 in the numerator, and then in the numerator times 1.6 times 10 to the negative 19 coulombs, all over 3 seconds. Okay? Look at the charge across it. Resistance is the opposition to current. Okay? It's what slows down your current. It's what uses energy. Resistors use energy to use the voltage. And if we recall, we have this formula right here. V equals IR. Ohm's law. Okay? If something follows Ohm's law, we call it ohmic, material-wise. If it does not follow Ohm's law, we say it's non-ohmic. What does that mean? It follows Ohm's law. We did graphs with this, if you recall from class. We looked at a graph of V versus I.
It could be like straight, then it could have a slope, or it could be non-ohmic, and then it then have the same slope all the time.
Yeah, it had a changing slope, and the slope was given by R. So if you recall, if a material is ohmic, let's think about, let's say we have an air conditioner, okay? I keep using that example because I always look up and see them. An air conditioner, and its internal resistance is 200 ohms. Overall resistance. Now, if that is true, let's say the voltage supplied is 120 volts. We can come up with what the current is, right? 120 over 200 is 12 over 20. That's going to be half of each, will be 6 over 10. So 0.6 amps. All right, that would hold true. Now, if the material was ohmic, if I double the voltage, the current should double, and this should remain the same. That's the idea of ohmic. Ohmic means that if the voltage supplied to that device changes, its resistance still remains constant. The resistance is a material property of the actual appliance. Okay? Everything that you use, every electronic device has resistors. Those resistors have some natural resistance. So as a result, this number should not change if a material is ohmic. If a material's resistance changes as the voltage changes, then it is not ohmic. And that was why we showed the curve like this. Because if you recall, the graph that we analyzed in class was this. It was V versus I, and the graph looked like this for an ohmic one, and the slope, if you recall, divide V by I, you get R. Right? Divide by I on both sides. I's cancel. You get R equals V over I. Well, that's change in Y over change in X. That's what this is. Change in Y over change in X. It's the slope. So the slope of this line is the resistance. So if you see a constant slope, it means the resistance is constant. So an ohmic material graphically would follow that kind of a graph. A non-ohmic material, since the slope is resistance and the resistance is changing, we have to look at the slope as a changing value. So you'll see that it's got a very low slope here at the beginning. And steeper, 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 steeper until it's very steep at the end. So this is non-ohmic, this is ohmic. It all goes back to, is the resistance constant? Constant resistance is this one, ohmic. Non-constant resistance is this one, non-ohmic. All right? So you can expect something like, hypothetically, right? For an ohmic material, such as blah, 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 whatever it is, the internal resistance is the following. If the voltage is this, what happens to the current if the voltage doubles? Well, you should know that if it's ohmic, this is constant. If the voltage doubles, the current has to double. These are directly related, voltage and current. Okay, voltage and current, more voltage, more current. The resistance should be constant if it's ohmic. All right? Let's see. What were the things that affected resistance? We talked in class in the notes. We had 4 things in our notes. Give me at least 2.
Actually, I'm not sure.
Give me 1.
Like, is it like the size of the glass?
Good. Which way? Size? What direction?
But
Okay. The cross-sectional area, also known as like the diameter. I wouldn't use width because it's cylindrical. Okay. The cross-sectional area of the wire. More cross-sectional area, less resistance. Think about it. Smaller cross-sectional area, it means there's more collisions. It's like squeezing water through a smaller area. You're going to have a lot more collisions. It's going to slow down the flow.
Smaller cross section, more resistance.
Marco? No.
Yeah, what was it? So smaller is
More
more.
resistance.
And temperature?
Temperature. As temperature goes up, resistance goes up. How do you remember that one? What was the one why I told you to remember that? Very simple. Very simple. More resistance means you use more power. A computer or a cell phone. When it gets hot, isn't it usually using a lot of power? You notice your power drains faster if you leave your camera on and the actual phone gets hot and heats up? You'll notice that. Now, obviously cold conditions can also drain power, but that's another extreme. It's a little different. The idea here, as temperature goes up, resistance goes up. What else? We got temperature, cross-sectional area.
Length of the wire.
What's the relationship there?
The shorter, the less resistance.
The shorter the wire, the less resistance. The longer the wire, the more resistance. Again, more room for collisions when there's a longer wire. It's going to collide a lot more, and as a result, slowing it down. Last thing. There's one more thing. Kian, what was the last thing? You had your hand up.
I was going to say that.
You're going to say?
Like,
Length. So we have length, cross-sectional area, temperature. Come on, this is the easiest one because there's no relationship really that exists. It's just another parameter. Copper versus nickel. The type of material. Very good. Okay, the material itself. Those are the 4 things that affect resistance.
wait, what did you say about temperature? The cooler, I mean, the warmer it is, the more resistance, right?
Yep.
And length is shorter.
Length it is, the shorter it is, the less resistance. The longer it is, the more
And
resistance.
type of metal or nickel or.
That's just, there's no relationship there. It's just, that's another parameter. All right. Let's see. What's the difference between direct and alternating current? Theoretical, obviously, kind of question. It could be multiple choice, it could be short answer. It could ask you to explain the difference between the two. You can make it into multiple choice and tell me which is which. Direct versus alternating current.
Opposite direction.
Direct versus alternating current, what's the difference? Julia, that doesn't matter.
It like flickers, like which you can't see, and it moves back and forth,
The charges.
the charges move back and forth or something, that's alternating, right?
Yep.
And then when it's direct, it's like, it just keeps moving.
Good. So a direct current would be the examples of the circuits we've looked at so far, where the battery has a fixed terminal voltage. One side is positive, one side is negative, and the flow goes, the positive flow, like we modeled, goes out the negative terminal and continues back to the positive terminal.
A direct current voltage.
Say again?
You said that a direct current has a battery with a direct
A
current.
direct current has a battery with fixed terminal voltages. Okay? Now, alternating current, like Julia had mentioned there, what's happening is those terminals are switching constantly. And I put up that example, and I showed you that, like, I think it was a solenoid or a magnet that was flipping back and forth, and you literally see the electrons doing this, back and forth. Okay, they gain energy, they use the energy. They gain energy, they use the energy. And what happens physically is there's a flickering, okay, when it comes to lights. But we don't notice that because the flickering occurs so fast. It occurs at 120 hertz, which means there's 120 flickers per second. In a second, like literally, 120 flickers just occurred, or 120 oscillations of light occurred. So we don't perceive it, okay?
So the electrons are constantly moving. What do they do? They're always.
They're like vibrating, they're oscillating back and forth, really. We talked about superconductors and potentiometers. You can expect that as like a multiple choice or a short answer. What's a superconductor? What's a potentiometer? Give me potentiometer. You should all know potentiometer.
Oh, yesterday we did it, the dimming the brightness.
Good. It's a variable resistor. It's a dimmer. Okay, a dimmer. That's what a potentiometer is. A variable resistor. What is
I don't
a
know, freeze it.
what is a superconductor? What is a superconductor? Yeah.
Just guessing. It's a conductor that conducts electricity without resistance.
Yes, it's a conductor when below its critical temperature exhibits no resistance at all. And the whole what's the word? Focus on it is that you start a current, you can remove the battery, and the current will continue to flow forever because there's no resistance. Okay? So a superconductor exhibits no resistance under a certain temperature. Let's see what else I want to talk about. We talk about the speed of electrons and things that are traveling through a circuit. What can you tell me about those speeds? If something fell, pick it up.
I know.
What can you tell me about those speeds? Like how fast do the electrons move in a circuit? You don't have to give me a number, but give me something relative. We talked about this in like 1901, I think. Nobody? Okay, the term was drift velocity. Anybody remember what drift velocity was? How to explain that?
It's like when electrons like bounce in like different directions.
Yeah, when the electrons are traveling through the circuit, they don't travel in a straight line. They interact with the metallic atoms in the actual conductor. Now, as a result, though, even though we turn the light switch on and it turns on instantly, the electrons still do not travel fast. They travel quite slow, actually. Remember, they travel at a very low speed. What is forcing the light to turn on?
That the circuit goes in.
Okay, but physically, yeah, the circuit is. But what is causing the actual circuit to flow? Remember, one terminal is positive, one terminal is negative. When you have two charges of opposing sign, you have an electric field that's always established between them. So in a circuit, because you have positive and negative terminal, you have an electric field that starts the motion of the electrons. The electric field is like a commander in an army that says, all right, like march, everybody start moving. The electrons start marching along slowly, a little bit at a time. And those electrons eventually get charged when they get back to the battery. And they move through the resistor very, very slowly. There's just a lot of them moving. So the light bulb can exhibit a lot of light because there's a lot of electrons, but they're moving very, very slowly. The electric field establishes its connection, though, at the speed of light. Okay? Make sense? So the electrons are not really traveling at the speed of light in a circuit. They're traveling much, much slower. All right. Let's see what else. If I gave you a circuit, you thought the circuit would run. For example, let's say we have something like this. So, discuss what would happen if this circuit were in front of you. Yes?
It's a parallel circuit.
R2 and R3 are definitely in parallel, right? Because there's a branching off after R1. So R2 and R3 are in parallel.
So it would reach R1 for sure.
Okay.
Turn on. It would reach R2 because the
Yep.
merge, I guess. It would, R1 would only go to R2.
Good. Why wouldn't it go to R3
Because
here?
it's an open circuit.
Very good. It's an open circuit on the right side. So the second branch wouldn't actually get any energy. So imagine like a parallel or a series or a combination of the two, and I'll put switches in certain places. So you need to tell me whether or not the resistor is actually operating. I'll put light bulbs. I'll say which bulbs would glow and why. Okay? So it might be more complex than this, but the idea that you have to analyze and understand what's physically happening.
Why can't the electricity flow like to R3 on the bottom?
Because it can't get back. Remember, it's got to get back always. You have to go through the bulb or resistor and out the other side back to the source. If you leave at the top, it doesn't get through there. Even at the bottom. Think about this splits, right? But eventually it's that open. Okay? All right. Now, another thing to notice, R1 and R3 are not in parallel. So how would you resolve this? You would look at these two in parallel first. Okay, I know these are in series. I understand that idea that they're in series, but they're not directly in series. There's a junction before they become in series, right? So we need to resolve this junction first. So you'd have to find the resistor from that, leave this alone, come up with an equivalent resistor in parallel right here, RP. So you'd have to do 1 over RP equals 1 over R2 plus 1 over R3. Come up with RP. You have a number now. Now these are in series. Say this was 10 and this came out to be 3. Add 10 and 3, you get 13. Okay, but again, you need to resolve things in the correct order. If we had something like this though, look at the upper circuit again, please. Another resistor here, R4. You then would resolve these two first by adding them because they're in series. You would replace that with one resistor in this location. Say this was 10 ohms and this was 3 ohms, 13 ohms, put one resistor, then do the 13 ohms in parallel with this one over here. Okay, I hope people are looking up because I'm trying to give you examples of this, and this is not the easiest thing.
So you just added R4, right?
Correct. Okay, had R4 been there, do this first, get a resistor, then do this in parallel. Series, then parallel, then one last series. You need to know your laws. You've got to know your laws. They're on the formula sheet, but you need to know what they mean. Okay, so in parallel, we know that the voltages are all the same, but the current is split up to each resistor, and that the the resistance are reciprocal sums. In series, the current are all the same, the voltage is split up to each resistor, and the resistance is the sum of the resistances.
Does the flow only have to go back to the source when it's a battery and not like a wall?
No, both.
Both?
Yeah. That's why there's two prongs.
But
You plug in as two prongs.
But how come there's a, like, in the textbook, there's like a distinction between like a battery and a dynamical ball?
One has a circle around it, that's the only
It
difference.
doesn't matter.
Yeah, there's a circle, imagine that symbol, put a circle around it, it becomes a plug. Okay? Yeah, but plugs and batteries act the same way. There's always two terminals, there's always a lead, there's always a follow, comes back after. What does it mean to dissipate or use energy? Dissipate or use energy in a circuit. When I ask you what dissipates or uses energy, what would you think of?
Light bulb or something.
Yeah, some sort of resistor, right? Light bulb, air conditioner. Give me examples of things like that. Be able to do that. It's called a load-bearing element. The amount of voltage that it supplies is called the load. So it can bear that load, meaning it can use that value, that amount.
Fridge does that.
The fridge, yeah, exactly. Any electrical element that uses electricity is a load-bearing element. What is a short? What is a short? I'm abbreviating short circuit, but what's a short?
When it blows.
Yeah, when it becomes overpowered and it has to release the excess energy.
Yeah, that's a good way to put it, but specifically it has no what? What is it missing if it becomes overpowered? A resistor. There's no resistance or resistor. So a short would be like this. You would never design something like that. Here's your resistor. There's nothing, I could call it R1, that doesn't matter. There's nothing that is stopping this flow from just doing this and saying, you know what, why would I go there when I can go here, right? This is the path of least resistance. That's called the short of the circuit. This wire would probably begin to overheat, and as a result, there would be no resistance. Well, I mean, it would overheat, which would increase the resistance of the wire, which could cause it to burn. But your little circuit breaker that's right here, the circuit breaker would sense a surplus of current. Because what's going to happen is this. The flow would just go right back. It wouldn't go this way. It wouldn't take this path and slow down and slow down. That wouldn't happen. So it would be too much current. The circuit breaker would detect all that current and flip open to turn the circuit off.
And wouldn't that happen too if you had another resistor in the middle?
For example,
If you had one,
like here,
No, on the red line,
yeah, on the red line?
in the middle,
One on R1.
R1 and R2.
Yeah,
like here,
yeah, like there.
that's not a short.
Why not? Why
Because now
not?
you have a resistor. This resistor regulates the flow of electrons through this piece or portion of the circuit. This resistor keeps and limits the flow of electrons to that portion. For every branch of a parallel circuit, you need at least one resistor on it. Any branch of a parallel circuit without a resistor is a short. That's what a short is doing. It takes another path. Like if I did this and then drew another line in, so now we're good. But if I did this, now we have a short. If I even didn't do that, right? Say I didn't do that. Say I did this instead. That's a short, actually. The path would do this.
Wait, why is that a short circuit?
Because the electrons choose the path of least resistance. It would not choose to go here. It would be like having a dam, then emptiness, and then another dam left next to it. Where would the water go? Would it go through the dam? It would go through that opening in the middle, wouldn't it? That's the opening in the middle. Okay? So, the way you can think of an analogy. We have a few formulas we used that are very useful. How much time? Give me a number.
13.
How many minutes left? 12 minutes left? 13 minutes left? Okay. So we've got Ohm's law for an appliance. We've also got our power formulas. Okay, we've also got our power formulas. We have the other formula that told you, and you have to recall this, or this is from earlier in the year. Okay, power is change in energy over time. So if you want to find the amount of energy used by an appliance, multiply the power times the time. Then you can find the cost of running an appliance by taking the amount of energy times the rate.
This is a quiz question.
Yeah, this is like this math we did on the quiz. The math you can expect, okay? The quiz math for sure. The math from section 20-2, where we had like a parallel or a series circuit only, and you had to calculate the equivalent resistor for all four of those resistors. Then you have to find like the current through each of the resistors and stuff. Expect a 20-2 math problem. The ones we did in class are perfect examples for that. Okay?
Sorry, what is equal?
Power equals change in energy over time.
What does that represent? Just the rate?
If you need to know how much energy is used by an appliance, and you know the power rating of the appliance and how long it's been on for, you can multiply power times time, and you get energy. That's from earlier in the year, with mechanical energy, we listed that one. Okay, but it's the same formula that provided. So yeah, 20-2, know how to do those several things. 20-3, know how to take a complex circuit and make it into a simple circuit with one resistor. Okay, what you did at the end of the lab, number 9, that's sufficient. What we did in 20-3, that example problem, that's sufficient as well. Okay, studying those is good.
When does the lab do?
It's on Moodle, I forget to be honest. I put it on there.
Oh, is that the test?
I think I put it due on like Tuesday or Wednesday. The classes are different though, so check your section too. The other section is due like I think a day or two after you because they're not doing their lab till today actually. They haven't even started yet.
Wednesday's day 6.
So it's probably Tuesday for you guys and Wednesday for them. Okay? But keeping in mind though, obviously that you're pretty much done with the lab. You should only have number 9 left at this point. If you didn't finish something in the lab, what do you need to do? Come in during a free, grab one of these resistor boxes, either do it here or go to another room and finish it off. But I think, has any group not finished, honestly? Jack, your group finished at the end there the other day?
Yeah.
You were, I think, the last group to go, that's why. I saw you guys were done for sure. Summer, your group was done for sure. Johnny, you were with Andrew, right? You were with them. Andrew, you were with Peter and Dirks? And the 3 of you are good? So everybody's good with this for now?
11th, do the 11th.
If somebody wants to help Victoria out on like Monday or Tuesday, wants to help her out with the lab and go through it with her, you're welcome to come in and just do that. Okay? I mean, she could ask me, but if you want to help her, one of your friends, you know. All right, so if I want to think about units real quick, and I'm doing a word problem, and something is given watts. Thank you. If something is given in watts, okay, the power is always given in watts. So you might calculate the power with one of these 3 formulas. Say you get 280 watts as the power consumption of that appliance, and you want to know how much energy it uses. Well, you take that upper right formula, you rewrite it as energy equals power times time. But what do you put in for power? Do you put 280 watts?
No.
What do you put? 0.280 kilowatts. Okay, I'm doing this because honestly, power is always measured in energy is measured in kilowatt hours. The time period, whatever T is, say it's 5 hours, goes here, and you get energy. So energy, the units of kilowatt hours are really the same thing as if you had like joules, just different units. But these are the units you want to use for electrical energy, kilowatt hours. We looked at a diagram several times of a battery hooked up to a bulb with the potential energy versus charge graph next to it. And I went from like point A to B, B to C, C to D, and then back. You should be familiar with that and be able to either explain it or answer multiple choice questions based on it. That's pretty much it. That's everything on the test.
That's a lot.
Okay, it's a rather long test, I think. A lot of material. I don't think it's a super difficult test, though. I haven't made it yet, so I don't know how many points it's going to be as it is. I always look at last year's test whenever I just review stuff. So I have an idea of the topics, and then I vary questions. So let's talk about that egg drop experiment. Did I go over it at all with you guys? Did we start talking about it? Nothing? Okay. So it's under documents and handouts. Open it real quick.